Assalamualaikum warahmatullahi wabarakatuh. We are from Group 2 of CSX USU in Image Processing. We would like to present about our project title called Tomato Leaf Disease Classification using Convolutional Neural Networks, or as we call it, CNN. Our project is presented by 5 members, one being Abdullah Muhammad Hatta, Amri Citra Wahyuni, Aji Muhammad Segi Praya, or that is me, Felix, and lastly is Sembiring Ekalma Toto. When we move towards the content, for the first part is introduction. Tomatoes are important vegetable crops grown all over the world. However, it can be damaged by many various diseases. Knowing the types of the disease is very important so that the farmers can treat their crops in a timely manner. It has been observed that leaves are a clear indicator of certain disease. Technologies such as image processing with deep learning methods have been developed to detect this disease. Our project is called Tomato Leaf Disease Classification using Convolutional Neural Networks, or as we call it, CNN. Propose 6 types of classification for lightweight CNN models consisting of 5 types of disease and 1 healthy condition in tomato plants. Second part is the objectives. To implement image processing steps in the tomato leaf image. Next one is to perform deep learning method, which is convolutional neural networks or CNNs to classify tomato leaf disease. And lastly, to develop a lightweight model that can predict tomato leaf disease. For the third part, data collection will be presented by our friend Felix. To Felix, I give it to you.
Okay, so for data collection in this project, we are using the dataset called Tomato Disease Multiple Source, uploaded by Kasim Khan on Kaggle. There are 6 classes used in this dataset. There is 5 class of tomato leaf disease and 1 healthy one. Diseases of them are late blight, septorial leaf spot, 2 spotted spider mite, tomato yellow leaf curl virus, powdery mildew, and the last one for the healthy one is healthy. To avoid overfitting, it is recommended to divide this observation into training and testing data. It is divided into 80 and 20%. For the 80% is training data and 20% is testing data. In the first step, we need to set the parameters for the models is using the training data. After that, we compare the model predictions for all testing data points with what was actually observed and use this comparison to gauge the accuracy of the model. For the training dataset is actually the dataset that model sees and learns from this data. The amount of image from the training dataset is 11,072 image. The next one is testing dataset. Testing dataset is the sample of data used to provide an unbiased evaluation of a final model fit on the training dataset. It is only used once a model is completely trained. The amount of image in this testing dataset is 2,740 images. The next part is flowchart will be presented by Chitra Kamri Payun.
Okay, the next for the flowchart. The flowchart of this convolutional neural network method is first here. We extract the data layer, and the second one is we splitting the data, which will be training data and also the testing data. And also the third process is building our CNN model. And after we building the CNN model with the configuration, and then we train the model. And the next is evaluating the model. And in here we check has it the highest accuracy rate that we want for our model. And if it's not reach the highest accuracy rate, we go back to build our CNN model to make some configuration, to change some configuration, and retrain our model and back to evaluate again our model.
And if it already reached the highest accuracy rate, we testing our model with the testing data set, and then we evaluate again with the test accuracy, and then we complete our model, our building.
Towards the model CNN. For the next one is the method and model architecture used in this project will be presented by Hatta.
Thank you for the chance, Chitra. Now I would like to explain methods or model architecture of this model. A convolutional neural network, or CNN, is a type of deep learning model that is well suited for image classification tasks. Here's the detail of the convolutional layer that we are applied. The first convolutional layer has 48 filters instead of 16 filters, and the second convolutional layer has 48 filters instead of 32. Third layer has 32 instead of 16 filters, and we are also using dense layer. The first dense layer has 128 neurons instead of 256, and the second dense layer has 64 neurons instead of 1 neuron. This difference in the model architecture will likely result in a different performance for the model. The model with 48 filters in each convolutional layer may be able to learn more complex features from the data. And for this model, we are using two layers for the extraction filter. The first is completely or convolutional 2D dimension layer. This layer applies convolutional operation to the input image, and the second is max pooling 2D. This layer downsample the output of the convolutional layer by taking the maximum value from each patch of the output. The model architecture also has two dense layers. The first is dense layer. This layer applies a fully connected layer to the output of the convolutional layers, and the second is this layer, a fully connected layer that has fewer neurons than the first dense layer. The model can be trained on a dataset of images of tomato leaves with different disease. Once the model is trained, it can be used to classify new image of tomato leaves. Next, we are going to input. So after we build the deep learning model, we save it, and then we can use it to input the image that we want to detect the disease. This function takes two arguments, a trained model and an image. The function first reads the image from the file system and resizes it to 255 multiplies 255 pixel size. The resized image is then converted to a NumPy array and passed to the model for prediction. The model returns a list of predictions, which is used to determine predicted class and confidence level. The predicted class and confidence level are then returned by the functions. And next, for the process. The third process is feature extraction layer. Extraction is the process of gathering and preparing data for use in a machine learning model. These may involve cleaning the data, removing outliers, and converting it into a format that the model can understand. Here, the extraction layer are involved in importing necessary modules, enhancing GPU performance, removing the dodgy image, loading datasets, scaling datasets, and splitting datasets. And the next process is classification layer and build the learning model. Classification is the process of assigning labels to data points. This is typically done by training a machine learning model on a datasets of labeled data. The main process of this layer is to define the model, train model, and evaluate the model. While defining the model, here's the summary of the process. Maybe we can next to below. All right. After defining the model, we would like to train the model. The code first trains the model on the trained dataset for 10 epochs. The validation data argument specifies a separate dataset that is used to evaluate the model's performance during training. The callbacks argument specifies a list of callbacks that will be called during training. In this case, the only callback is a TensorBoard callback, which will write the model's training and validation history to be a TensorBoard log file. Can continue. The fit function method returns a history of the object. So it will display the history of learning rate, which contain of record of the model training history. Next, we also evaluate the model after we training it. So we could see that the loss rate of the each epoch is decreased by the time, and the accuracy is increasing. Next, from the last process in classification, the model could classify 6 different class of the data sets. Okay. All right, for the output. Here's the code for displaying the output. The output we want to see like down below. We would like to see it in the sample. First, we can, sorry, Citra, and you can, all right. And in the input image, we can input the image that we want to predict. For the first test, we are using file named healthy.jpg. And for the second image, we are using file named spider. And the output is, for the first image, it's predicted the class is healthy. So it means the leaf should be healthy. The confidence is 87.72%. And for the second output of the image is predicted to spider mites, two spotted spider mites. Confidence is 87.72%. So I think that's all for the model and the architecture. Thank you. I give it back to Aji.
Right. Thank you, Hatta. And here I would like to show you our source code. Then we continue to the next part is test and evaluation. All right, I'm sorry, we will move towards the system demo, which will be presented by Citra Wahyuni Amri. Citra Wahyuni, I give you the authority.
Okay, thank you for the time, Aji. We next to the system demo. So here the source code of our model. Okay, from the first step that we import necessary dependencies that will use to make model. And then this code means that like we are limiting the GPU or VRAM that in our machine to use in this model, because we don't want that will be memory errors or OOM errors. So we setting the GPU memory consumption growth using by this system. So we just run the code. Okay, and the third part, our third step is we are removing the dodgy images, because we don't know that our dataset is contains images that are not suitable for this Python, for example, for the extensions or for the maybe corrupted in some cases. So we just don't want that will happen in our system. So basically, we are running this code, and basically this code has kind of several seconds to run. So we just skip this step, because we already have the train model that we are saved. And the next step is to loading our data. So here we have the directory data, and it have this 13,000 of images that belonging to 6 classes that we want to classify. And then we just run the next code. Basically, this is loading our data and changing it to the NumPy array. So here our images is shown as the array, and here we have the length of batch is 2, which means the first batch, the first index is used to save our images, and the second batch is used to save the label or the name of the classes. So here is when we type in the batch 1, it means like it defines our classes from index 0 to 5. It means it defines the 6 classes that we want to classify. And here we show our images from each batches, like this, from index 2, index 1, and etc. So the next step is to scaling our data. Scale means like we want to divide our images by 255. So we have the minimum value 1, minimum value is 0, and max is 1 instead of 2 and 255. So we so we check the max of our images. Max value is 1. And we want to do that for each images in each pages. So we use this data map. So here is define our images. We want to define the branch and Y is our target, which is the label or the class names. You want the code? We will show our images again. So we check again. So we have these images with a maximum is 1. And the length of our data, which 40,153 pages. So the next step is split our data. So we want to divide our data into the training data, the validation data, and the testing data. So training data is data that used to learn by the model to predict our testing data, and the validation is data that used during the training to see how the performance of our model is, and the test is the post training that we will use later. So we run the code and we define the size of the train and validation and testing data, which explain that we have 80% of data to train and the 20% for the test, and we divided also the validation size. So we, for example, we check the line of the training data that we have 346 pages. So the next step is building our deep learning model. So first we define our model by sequential model, and then we define the convolutional layer and also pooling layer that have been explained by Hatta before. Like we train the code, we run the code, and also we compile with the optimizer and also the metrics. And you can see the summary of our model that also has been explained by Hatta before. And the next is we want to create the log layer, and here is where our model is trained with the info is done. So because this takes time, we also skip this step because we already trained the data and have set the model itself. And here is the evaluation that we already did, and this is also the evaluate performance. And the next is testing. So we need to load our dataset again, and then we loading the class names. We have these six classes, and then we define the predict function to predict the model, to predict the images using the model that has been trained. So here, but we will use the set model, the model that's already set. But before that is the test accuracy that we achieved, that which is the sorry. Okay, actually this is the set model that we already achieved. This is the define the new model. So we predict using our new model that has been saved. And we run this. And here we load this spider.jpg and we see the result. So yes, this model successful to predict the class of the spider, two-spotted spider mite image that we load. So I think that's all from the demo of the system. And back to Aji.
Thank you for our unit summary. We continue towards the next part, which is test and evaluation. Here are the results of our test and evaluation. You can see here. All right, the test and evaluation will be presented by Felix. So Felix, I give you the authority.
So the next part is test and evaluation. There is the first one is accuracy rate. Accuracy rate is defined as the ratio of correctly predicted instance to the total number of instances in a dataset expressed as a percentage. It means how accurate the result is. And for this project, for this model, this project gets 97% of test accuracy. The next one is learning rate. Learning rate is viewed as the absolute hyperparameter to tune and remarkably influence model training with gradient descent algorithms. As for the to calculate the learning rate for each approach, you can use the following formula: is learning rate equals initial learning rate, and so on. Based on the formula given above, the first learning rate for our model is 0.008 or 0.8, and the highest learning rate is 0.01 or 1. The next one is error rate. Error rate is a measure for the performance of a CNN. A lower rate indicates that model is performing better, and if the error rate is higher, it means that the model performance is worse. There are several factors that can affect the error rate, including the size of the data set, the complexity of the model, and the optimization algorithm that is used. And for the next part will be presented by Eko Matoto Sembiring.
Okay, thank you, Felix. The next part of text and evaluation is the recall. Now, recall measures the proportion of actual positive labels correctly identified by the model. So, recall is helpful when the cost of false negative is high. So, a hard false negative has devastating consequences. Okay. And the next part of the test and evaluation is precision. Precision is too helpful when the cost of false positive are high. So let us assume the problem involves the detection of skin cancer. If we have a model that has a very low precision, then many patients will be told that they have melanoma, and what will include some misdiagnosis. So a lot of extra tests and stress are at stake. And the next part is conclusion that I conclude the proposed system 5 main biases of tomato livers. So the conclusion, the next is lead bright, septorial leaf spot, powdery mildew, spider mites, and yellow curl are detected using multi-class classification of culture convolution neural network or CNN. The system is able to detect with the test accuracy 97%, and future work includes extending the number of disease classification of virus disease along with the virus species. Uh, improving the accuracy, developing a system that will help in automatic capture, detect and classify the disease and take necessary action using suitable hardware and software requirements. And we go back to moderator, is Aji.
Right, thank you for recommendation Engineering, and these are our that is all of our presentation for today. I'm sorry if perhaps our presentation exceeds the limits of 20 minutes. I would like to say thank you again to us, Mr. Ahmad Fikri Anwar, for the time we are having for this presentation. For our mistake in words, we would like to say sorry. Wassalamualaikum warahmatullahi wabarakatuh.